Texas Lutheran University.
Welcome to the special homecoming edition of Senior Sen. Today we have Nichole Pollok, who you may or may not know, related to the other Pollocks that are populating the room right now. Nichole got her undergraduate degrees plural. What did we decide, 3 years ago in May?
Yes,
Something
sure.
like that. In molecular biology, but more importantly in chemistry, and has since gone on to work on her PhD up at UT Austin, doing somewhat analytical electrochemistry, mostly electro.
It's all analytical though.
Okay, well that's good. I'm glad you went down that path. So Nichole's going to tell us a little bit about what she's working on.
All right, well, thank you for the introduction. I'm Nichole Pollok, and I work in Dr. Richard Crooks's research group. We are primarily an electrochemistry group. We do a lot of electrocatalysis. We make a number of microfluidic devices and also a number of sensors and with various applications. So today I'm going to be talking to you about the electrochemical detection of silver nanoparticles by galvanic exchange for point-of-care applications. So some point-of-care devices that may look pretty familiar are, for example, the home glucose meter and then also the at-home pregnancy test. So the point of these devices is that they are very inexpensive so that you can do multiple tests a day or a week if you need to. And then they also need to be very user-friendly so that the patient isn't having to do too much interaction with the device before they actually get the information they want from it. These are used in both developed and developing countries. So our potential point-of-care device is the no-slip, and this is something which looks like this. So this is something that we want to eventually be able to use to detect a heart failure biomarker with. So this is what we call the no-slip right here. It's called a no-slip because a previous version of this device actually did have a slip layer to it, so that the patient would have to pull the slip layer, and that was a little bit too interactive, we thought, so we kind of scrapped that. So this is a device that is printed on a piece of chromatography paper, and then it has various folds to it. And since we are an electrochemical group, we use electrochemistry to detect our analyte. What you'll see up here is a working electrode that has gold deposited on the top of it. We have a carbon quasi-reference electrode and then also a carbon counter-reference electrode. Going into a bit of the fabrication of our no-slip device, first step, like I said, is we go through and we wax print these chromatography papers with a pattern like you can see right here. These actually do only have the third layer to them because we got rid of the whole slip layer portion. After that, we go through and we melt the wax. So after the printer has gone through and sprayed the wax, we put the paper in the oven for a little bit, for 25 seconds at 130 degrees. And what that does is that melts the wax that was initially sprayed on top of this paper surface, and it seeps through a little bit, which then it makes a bit kind of something like a channel to it. So since the chromatography paper is pretty porous, these wax molecules can find their way through the whole depth of these through these devices. Next, what we do is we walk it over to the laser cutter, and what we do is, well, here you can see it cut out from the big sheet, and then we go through and cut out these warded pieces as well. And to get our carbon electrodes, we actually stencil print these electrodes on the paper surface. So we use conductive carbon paste, and these are traditional screen printing techniques. We have a substrate, which is the paper on the backside, and the support is usually either the table if we're wanting to be messy, or a piece of glass so that we don't get too much carbon paste on the table. And then we have a stencil that we put on top, and the stencil looks something like this. So then we have the carbon ink on top, and we smear it across, and you get the imprint of the stencil. The next, what we do is we go and electrodeposit gold at this working electrode area. So what the gold does is it's going to be our stable oxidizing agent for this device. The previous device that had a slip in it had a permanganate oxidizing mechanism, which the potassium permanganate isn't very stable at all for very long amounts of time. You can see the final product sitting right here. So this sheet right here folds under the back that way, and then this folds over the top of it so that you pretty much have a bowl for these electrodes to be sitting in. Some key features of this device is the hollow channel right here that we go through and laser cut also. And then the hollow channel allows for quick fluid transport through this device. So this spoon-looking portion is what we call a Hemi channel. So it has a little bit of wax on one side and has a hydrophilic layer on the other side. So that allows for some capillary flow of sample that would go into the outlet, the inlet right here, and then flow down the channel and then into the outlet, and then the excess material will be caught in the sink area. So, here we go. Here's a nice little interactive. So this is a video that was put together by a previous group member, and what you're seeing here is the 4-layer device, but we're doing the same thing but just with 3 layers. So what you just watched is you saw sample flow from the inlet down to the outlet, and the rest of the excess ended up in the sink. So also what you're looking at here is this is the working electrode that I showed y'all a second ago, and then our quasi-carbon reference, and then our counter reference right next to it. And this back here is a magnet. So zooming in on this even more, what we have is what we call a model composite. So to make this model composite, we have a magnetic microbead that has a streptavidin coating around it, and then we go through and we conjugate that with a silver nanoparticle that's been biotinylated. And because of the binding constant between the streptavidin and the biotin, we get a model composite that is in one piece over here like that. So the point of the magnet itself and the point of having magnetic beads is so that we can have a bit of a pre-concentration step before we do any of our analysis. Also, instead of using some type of an enzymatic label, we use a silver nanoparticle label, which is also another source of amplification. Moving along, so what we do after all the sample has been flowed through, we apply a potential, and then gold is oxidized off of the working electrode. You can see a little bit is still on there because not all of it comes off. The gold is actually in excess in this system. And then what that does is it galvanically exchanges with the silver nanoparticles on these magnetic beads. So as you can see here, the gold is now sitting on these beads, and we have silver ions in solution. Next, we go through and deposit those silver ions back onto the working electrode. You can see the little layer right here. And then finally, we use anodic stripping voltammetry, and we strip off the zero-valent silver and put the silver ions back into solution. And when we do that, we get a trace that we're able to integrate, and we're able to translate that back to how much silver is actually in the system and how much silver we're picking up. So this is a current versus potential trace, and we integrate the area in here, which gives us the silver charge. All right, so we've been running into a lot of problems with this no-slip device. There's been a number of challenges, so we've been doing a lot of troubleshooting. Some of the problems include poor reproducibility. Some of the magnetic beads get lost when it's being flowed down this lateral flow channel. And also the silver charge is relatively low, which this could also all be attributed to beads not actually getting to the working electrode surface. So to start figuring out what the heck is actually going on, we went ahead and made a different type of holder that really secluded just the electrode portion of the device. So what you're looking at right here is, again, the gold deposited working electrode. And instead of flowing our model composite in solution through this device, we're now drying a set amount at the working electrode just so that we're not losing any beads. Another thing that we're doing is we're doing all of this in what we call control holder 1, because there again is no flow, and we're also using a real mercury sulfate reference electrode. The nice thing about the real reference electrode is that the silver peak, whenever you strip it off, it stays at the same potential each time. The only difference between that and the carbon quasi-reference electrode is that the potential that the silver comes off at bounces around a little bit. So that peak that I showed you just moves around a little bit on the graph. And then also we have a real platinum counter wire. To even further ensure that we're not losing any beads in our system, we also have a magnet on the back side of this device that sits right underneath that working electrode. And our supporting electrolyte is a borate sodium chloride solution, just so that we can do all of our electrochemical detection. Okay, so with this device, with this controlled, very, very controlled optimization vehicle, we were able to manipulate our different electrochemical parameters. So the amount of time the gold was oxidized, the amount of time the silver was deposited, and then some of the other aspects. Another thing we wanted to look at was we wanted to see what was actually happening to these silver nanoparticles when they were on these magnetic beads and all of these electrochemical processes were happening to them. So after each of the electrochemical steps that I showed y'all, we took SEM images of the composite on the working electrode, just so that we can see what's going on. So what you're looking at right now is the streptavidin biotin conjugate with SEM. So you can see that it's a 2.8 micrometer bead, and it's very heavily decorated with these 20 nanometer silver nanoparticles. So the only problem with the 20 nanometer silver nanoparticles when we're trying to look at all these images with SEM is that they are so small that you're actually not able to see the morphology of these particles on these beads. So for these experiments, we went ahead and conjugated a 110 nanometer silver nanoparticle instead. You can see they're nice spherical silver particles. These are citrate cap silver nanoparticles, so they don't really aggregate too much. So with this, we went ahead and did all of our electrochemical steps, but with bigger nanoparticles, so we can see the morphology of these particles on these beads. So prior to doing any EChem, what we wanted to do is we wanted to look at these beads on a TEM grid, so a plain old nickel grid, and put it into the SEM and see what it looks like. And then also see what it looks like whenever we have it on our gold deposited working electrode. The main point of this was to make sure that we weren't having any of the silver nanoparticles exchanging with the gold on the electrode surface before we told it to, pretty much. So we went ahead and checked that. So for all of these SEM images, we also did elemental mapping. And as you can see, these particles right here, so the red corresponds with the silver, the green corresponds with the gold that's been already deposited on the working electrode, and these magnetic microbeads actually have an iron core to them, so we're able to see them with SEM also and get their elemental map. Unfortunately, using this is more of a qualitative than a quantitative approach, because we're just really trying to get a feel for what's actually happening in this system. And then also, the gold signal for this technique has a high amount of background to it. So it looks like you have a little bit of gold on the bead already, but actually you don't. So we took a line scan also of this bead, and as you can see, this green trace right here, which is the gold, you don't have any gold in solution. The only issue is that it's not camping out at 0. So the background for the gold is actually pretty high. Another thing you can see is this blue trace is actually following the shape of the bead, so that's the iron, so we know that that's the bead. And then we have this red trace, which are these that match up with the silver nanoparticles that are on the surface. Now I'm going to keep the same color scheme, so you're not going to have to be tracking colors throughout the talk. And also, like I said, our supporting electrolyte is chloride, or it has sodium chloride in it. So we're able to actually see chloride in this line scan as well. So there's a lot of steps going on with this. So in this bottom left-hand corner, I have a list for us to all follow together because there are quite a few steps. And then also a scheme that kind of correlates with what is going on in these images. So y'all just saw this image, and what this is down here is this is the gold that's been deposited on the working electrode. Here you have this blue is all corresponding to the iron magnetic bead. And then also the silver particles are on the bead as well. So this is just an image of the model composite dried at the working electrode with no ECAM. First, after that, we go through and we do some gold oxidation. So we have gold coming up off of the electrode. There we go. And this is what we think, because I just showed you another scheme about this is what we think is already happening, where it just goes up, floats all the way up through the bead, and then initially swaps out with the silver. So this is what we think is happening. So we have all of the gold still, we have the gold that all swapped out with the silver. So these are now gold beads, gold particles instead of silver particles. But when we look at our SEM, we don't exactly see that. So what you're looking at up top is you see not a whole lot of gold on the beads, but still a lot of gold, a lot of silver sitting around these magnetic beads. Another thing you can note is that there's really salty looking structures around this too. And we can kind of guess that it's silver chloride, it's chloride because we do have chloride in the system because it's part of our supporting electrolyte. But the only problem with, here's the rest of this. There we go. Okay, so the only problem with the silver chloride is that it actually acts as an insulator. So what this does is it kind of prevents the migration of the gold ions up through from migrating around the rest of the magnetic beads and the silver on those beads. So what we actually see with the SEM images is that we have gold oxidizing off of this electrode, but then we're making silver chloride in the process. So this prevents more gold ions from getting up to the particles further away from the working electrode and actually higher up on the bead. Next thing we do is we go through and we do silver deposition. And so that gold chloride, that silver chloride cloud comes back down, it's deposited on the working electrode. And what you see here is that, so this portion, this is the carbon electrode, and you can see that the particles that were closest to the carbon electrode actually did exchange pretty well with the silver that's on the beads. However, the particles that are a little bit further away from the electrode actually don't have any exchange happening to them. And also the scheme down here, we have some exchange and then some partial exchange with the silver and the gold. All right, so normally what we would do after this step is we would go through and do our anodic stripping and strip the silver off of the working electrode surface to see how much silver is actually on there. But since we were noticing that so many of these silver particles hadn't actually been touched yet, we wanted to go back and give it another dose of the gold oxidation and then the silver deposition again. So what happens this time around is we go through and oxidize the gold again. But this time we have even less silver chloride formation. So the gold chloride, the gold ions are able to migrate further up this magnetic bead and further exchange with more of the particles further away from the electrode surface. And that is kind of what we see in our SEM images. So what you're looking at is this is a gold and silver overlay of this image right here, and you can see that there's a lot of, there's not a whole lot of silver on these beads anymore. And that's because it's either already on the electrode or because it's being formed up with an alloy with the gold already as well. So after this, we went through and did silver and deposition again, so that silver chloride cloud comes back down, deposits on the electrode surface, and then we see, this is the STM images of the second gold after the second gold deposition step. And you can see that pretty much every spot where there is gold, there is also silver. So there's a lot of alloying going on in partial exchange. So these silver nanoparticles are so big that they actually don't fully galvanically exchange, but that's okay because we mostly just want to get them partially exchanged for right now. But the good thing about this is that mostly everything that is on the beads has some amount of gold and some amount of silver on it. So after this, we were kind of curious as to, well, we kind of thought that we had really improved this detection method. So we wanted to go about and actually make a dose response curve with this method. So the figure on the left is a silver charge versus silver concentration plot, and it is pretty linear. The dynamic range is from 2.6 femtomolar to 337 femtomolar. And this is very useful because if we want to be able to use this detection method for a point of care application, we need to have a fairly wide dynamic range so that we can tell somebody, okay, you're getting towards the red zone versus, okay, you don't need to worry about anything right now. So, and then also the reproducibility for this method is about 24% RSD, which is for this point. And then all of these were tabulated with 5 reps apiece. So, and to put this into perspective a little bit, the previous no-slip device had a much smaller dynamic range and was a lot less reproducible. So we've gone from 2.6 femtomolar, we've gone from 1.2 picomolar to 2.6 femtomolar, and also the reproducibility has improved greatly. The graph on the right is a current versus potential plot, and these insets are actually our lowest concentration. So these peaks are our silver stripping peaks. So when we go through and do our anodic stripping voltammetry, we go through and we have a current versus potential, and then we can integrate the area underneath these curves. All right, so coming back full circle, what we want to be able to do, since this device is working a little bit better now, we want to be able to take the same main pieces, so the silver nanoparticle and then also the magnetic microbead, and use the same pieces but use different glue. So what we want to do is want to be able to use antigen-specific antibodies to target and trap our target antigen, pretty much. What I've been working on recently is the NT-proBNP antigen, and this is one of the biomarkers for heart failure, and this is something that we've been trying to develop. And also another person in my subgroup is actually trying to do the same thing with HCG, so the pregnancy hormone, and then also the LH hormone, which helps track fertility and stuff like that. So yeah, this is what we end up really wanting to be able to do with this type of system. And so overall, we've been able to better understand our gold-silver galvanic exchange mechanism. We've noticed that there is a lot of silver chloride formation, but we can also remove it in the process. Something else we've been able to do is significantly improve our no-slip device. That was, I think that was published back in 2015, and we've fixed that by a whole bunch. We've dropped the LOD and also increased the dynamic range. And then, like I said, we want to be able to transition this back into full amino sandwiches to do kind of more of a plug-and-play aspects of different analytes for different systems to use with our composite, or our beads and nanoparticles. But, yep, here's my research group. So I'd like to thank Dr. Crooks for actually letting me work on this project. Another person, we have a collaborator, Ian Richards. He was actually one of the chief inventors on the clear blue pregnancy test, so it's pretty cool to have him as a collaborator with us. And then also Paul DeGregory, which was a previous group member. Molly Kogan and I have also, we did a lot of the SEM images together. And then my whole paper subgroup, and then the Crooks group in general. But
All right. Hit it with the question.
Every senior student has that question.
And epic fail.
Yes,
I went through that faster than I thought I was going to.
From here, now that you made these improvements, what's next?
Is to fix the immunoassay. So all these pieces back here, a downfall about having silver as a label for these things is that it kind of really also denatures antibody and other biological molecules. So the trick is finding antigens that are compatible with silver and then also are still really specific to our antigen. So yeah, so what I'm doing now is I'm going back and making sure methods for making this piece is optimized, so the silver and the antibody conjugation, and then also the magnetic microbead and the antibody that goes onto that piece, making sure that we're actually making that conjugate whenever we mix them together. But yeah.
Is this meant for like a drop of blood?
Eventually, yeah.
So these little nose clips are there's just one test and they're disposable, like a diabetes or blood sugar test?
It's all paper and wax and carbon paste.
Do a lot of people worry about checking whether their heart is failing on a daily basis?
Well, the methods that they use now. I mean, there are patients that, they're told by their physicians that they should watch their fluid intake and watch their weight very closely because subtle fluctuations in these can be signs of something really bad happening. And it would be nice for them to do a test like this that is more frequent instead of having to go to the doctor maybe every month, every 3 months to have everything checked out. And then also another plus about being able to monitor it more closely is that you can establish a basal level for these patients so that you can notice subtle fluctuations in these concentrations of analyte. So that then the physician can go and adjust the medication or adjust whatever else they're using to combat their heart failure.
It'd be nice if you had I'm going to talk first.
I've raised my hand. No, go ahead.
It'd be nice if you had, this is just an idea to float, if you can make a completely disposable unit, then just keep it at home. But you can do this and you can have like a heart attack test at home type of thing. So just to think, I mean,
A heart attack is different though too.
Yeah, I know.
Heart failure and a heart
But
attack is
it would be
different.
something that we can at least say that there's something wrong. If you see an
Yeah, because
elevated
there are,
level
I
of
mean,
this.
there's huge
Yeah.
chemical spikes that happen when you're having a
Yeah.
heart attack, as turns out.
Well, it would be watching the elevation of it also.
Right. Well, there's normal and abnormal levels. I mean, nobody's going to sit there and say, eating their cereal, I'm going to have a heart attack. No. There's other symptoms that are associated with that.
But also everyone's basal level is different,
Yeah.
especially if they're on medication. So,
But if they're not,
well, this is meant for people who already know that they have heart failure. This is meant to track something that they already know about, just so that they can have better patient care.
okay. Thank you.
Oh, you got one behind you.
No, go ahead first. Okay.
So would this give you like some kind of readout, or would you have to take it back to your physician so they can read it?
Eventually, this is all going to be something that is self-containing in a holder, and it'll be a scale from red light to green light. So you'll be able to, it'll be very.
You need a printed or not?
That's right.
Oh, I mean, there's yellow in between, but Something that, so the patient's not having to look at a digital readout of what's actually going on in their system. I mean, if it's red, they should probably get themselves over, call their doctor or something like that. Or even yellow, call their doctor, and then green, they've got nothing to worry about. But it's meant to be very not taxing on the patient itself.
So nothing like this actually exists right now?
Nope. And a bigger problem is that since there is no, so whenever you do go into the doctor and have this checked out, they have to do a blood test, and then that takes a while, and you have to actually have that done by a technician. You can't check that on your own anyway. And then also, what was your question again? Sorry.
Nothing like this like currently exists?
No.
That's the short answer.
Yeah.
Gonna ask mine now. So you get a precipitate when you use chloride in the supporting electrolyte. Have you tried another anion instead of chloride that doesn't precipitate with silver? Just curious.
We
Do you use chloride
have-
for a reason? Maybe there's a reason I'm not getting.
So there is chloride in our gold salt also. So, and then, so our supporting electrolyte is a borate sodium chloride solution, and it's a 100 millimolar of borate and sodium chloride. But I believe they've tried PBS and some other things, but
Yeah, to me, the one that comes to mind for me would be nitrate instead of chloride, because silver nitrate is soluble in water. You might minimize the precipitation if you. I don't know exactly.
silver isn't that
Silver
something?
nitrate's not soluble in water, or is soluble in water, I should say. Yeah.
Okay.
Yeah, because basically every silver,
Mm-hmm.
every silver complex is precipitates except silver nitrate.
And it also needs to be biologically compatible too. So, and also the end goal is to use blood samples, and there's a lot of chloride in the blood samples. So if we take care, we're going to have the chloride problem eventually. So we might as well take care of it now.
For more information, please visit tlu.edu.